So we want to look at the relationship between beta and gamma function. Of course, I've given you this relationship before. The beta of m n is equal to gamma of n all over gamma of m plus n. And I told you that we are going to be proving this much later. So in this video, we are going to be proving this. And we will also prove this as well. Gamma of p, gamma of p, gamma of 1 minus p. Gamma of 1 minus p is equal to pi all over sine p pi for 0 to be less than p, when p is between 0 and 1. And then we are going to be using this assumption, given that integral from 0 to infinity of s raised to power p minus 1 over 1 plus s dx equal pi over sine p pi. Later again, not in this video, we are going to be proving this. Our integral from 0 to infinity of s raised to power p minus 1 all over 1 minus p dx is equal to pi over sine p pi. So now the first thing, we want to show that beta of m, n is equal to gamma of n, gamma of n all over gamma of n plus n. So recall this. We know one of the form of the beta function, of the gamma function, is gamma of m is equal to z raised to power n integral from 0 to infinity of all these things that you have here. And this is where z is a constant in this case. Z is a constant here. So recall from, I think, from 3 of the gamma function. So that's where I'm going to start from. Now it means that gamma of m, take this z to the other side and let's enter the integral. It's a constant from 0 to infinity of e raised to the power of minus zx, z raised to the power of m, s raised to the power of m plus m minus 1 dx. That is what I'm going to have. So I will now multiply both sides. By e raised to the power of minus z, e raised to the power of minus z, and z raised to the power of n plus 1 or n minus 1. So I multiply both sides with this so that I have gamma of m. Then I have multiplied by e raised to the power of minus z, z raised to the power of n minus 1 equal integral from 0 to infinity of e raised to the power of minus zx, z raised to the power s. Then all these ones too, we enter the integral. Multiplied by e raised to the power of minus z, z raised to the power of n minus 1. Then I have s raised to the power of n minus 1 ds. So let me write it well. I have gamma of m. So in reality, what I've just done here is I've multiplied both sides by this, and this is a constant under this integral, so I can allow it to enter the integral. So I have gamma of m e raised to the power of minus z, z raised to the power of n minus 1 equal integral from 0 to infinity. Now this is e raised to the power of minus zx, e raised to the power of minus zx. I can write it as e raised to the power of minus x plus 1 z, e raised to the power of minus x plus 1 z. Again, I have x, z raised to the power of x, z raised to the power of m instead, z raised to the power of m. Then this one I have multiplied by z raised to the power of m plus n minus 1 multiplied by s raised to the power of m minus 1 dx. That is what I'm going to have. Just follow through what we are doing. We are just we only multiply e raised to the power of minus z raised to the power of n minus x. You will have it here. So this is what we have. Then I will integrate both sides with respect to z from 0 to infinity. integrating both sides with respect to z on this interval 0 to infinity. Between 0 and infinity, let's integrate on that interval. So what I'm going to have is I will have integral from 0 to infinity of the gamma function of n, then e raised to the power of minus z multiplied by z raised to the power of n minus 1 dz is equal to integral from 0 to infinity, another integral from 0 to infinity of e raised to the power of minus x plus 1z multiplied by z raised to the power of n plus n minus 1, then x raised to the power of n minus 1 multiplied by ds and as well as dz. That's what I've done to both sides. So gamma of n is a constant inside this integral. Let it come out. This one will become gamma of n. Then I will have integral from 0 to infinity of e raised to the power of minus z multiplied by z raised to the power of n minus 1 dz is equal to, now I can write this as integral from 0 to infinity, then open a bracket, integral from 0 to infinity. I want all the ones that have z to be under this integral. This e raised to the power of minus x plus 1z multiplied by z raised to the power of n plus n minus 1 dz. Then outside the integral will now have multiplied by x raised to the power of n minus 1 dx. So this is exactly gamma function, gamma of n. So this is gamma of n. Then this other one you have here is gamma of n. This one will be integral from 0 to infinity. Now, what we have under the integral? Don't forget, mind you, remember that integral from 0 to infinity of e raised to the power of minus kt and t raised to the power of n minus 1 dt. We have done that before. That was one of the form we proved. In fact, that is what I have written here. This is the constant z. This one will be equal to gamma of n all over k raised to the power of n. In fact, that is what I used at the beginning of this proof. So that's what I'm going to use here as well. Now, if you let k, look at it, if you let k to be x plus 1, and this n to be just n plus n, just replace n with n plus n, you will see that this one will become integral from 0 to infinity of e raised to the power of minus k is now x plus 1. That will be minus x plus 1t multiplied by t is tt. I have t raised to the power of n minus n. I said let n be n plus n. So this one will be n plus n minus 1 dt. So the answer to this will be equal to gamma of n, but n is now n plus n. That's gamma of n plus n over k. K is x plus 1. X plus 1 raised to the power of n. N plus x plus 1 raised to the power of n. But n is n plus n. So that's what I'm going to have, n plus n. So that means in this case, the integral of what is in the bracket, all these things here, is exactly gamma of n plus 1, n plus n over x plus 1 raised to the power of n plus n. Then outside the integral, I still have x raised to the power of n minus 1 ds. So at the end of the day, I have gamma of n. Now, gamma of n plus n become a constant in this integral, so it can come out. It is equal to gamma of n plus n integral from 0 to infinity integral from 0 to infinity of x raised to the power of n minus 1 all over x plus 1 raised to the power of n plus n dx. The variable side by gamma of n plus n. So I will have gamma of n over gamma of n plus n is equal to, then I have integral. All this integral I have here, this is integral from 0 to infinity of x raised to the power of n minus 1 over x plus 1 raised to the power of n plus n. If you look at the form 2 of the beta and gap of the transformation of the beta function, you will see that this is exactly beta of n plus 1, n comma n rather. So therefore, I have gamma of n all over gamma of n plus n to be equal to gamma of n all over gamma of n plus n to be equal to beta of n comma n, and we have proved this one. So it remains the second one. So it remains the second one. Let's prove the second one, number 2. We have proved number 1. Number 2 is saying that beta of p, comma 1 minus p equal gamma of p, gamma of 1 minus p is equal to pi over sine. And they ask us to use that, given that integral from 0 to infinity of x raised to the power of p minus 1 over 1 plus x dx is equal to pi over sine p.pi. So in this case, over here, recall that from gamma of n equal to gamma of n plus n is equal to beta of m comma n. So just let m to be p and then n to be 1 minus p. So this one will become gamma of p, gamma of 1 minus p over gamma of 1 is equal to beta of p 1 minus p. So gamma of 1 is 0 factorial, that is 1. So I have gamma of p, gamma of 1 minus p to be equal to beta of p comma 1 minus p. So that is what I proved this. Now this is equal to integral. Don't forget, beta of m comma n is integral from 0 to infinity of x raised to the power of m minus 1 all over x plus 1 raised to the power of m plus n dx. So this one will also be integral from 0 to infinity x raised to the power of m, but m here is p. So I have p minus 1 all over x plus 1 raised to the power m plus n, that is p plus 1 minus p, which will give me 1. P plus 1 minus p dx, which will give me 1. So it then means that gamma of p, gamma of 1 minus p is equal to beta of p, comma 1 minus p equal integral from 0 to infinity of x raised to the power p over 1 plus x dx. But I have been given here that this one is equal to pi over sine p.pi. So therefore, gamma of p, gamma of 1 minus p, which is equal to beta of p, comma 1 minus p equal pi over sine p.pi. That is what we have. That is the solution to the second one. So later we will show how integral from 0 to infinity of x raised to the power of p minus 1 all over 1 plus x dx equal pi over sine p.pi. We are going to do that next time. So I want to, let's do some examples here. worked examples. Number 1, beta of 1 plus n, 1 minus n is equal to gamma of 1 plus n, gamma of 1 minus n is equal to n pi over sine n pi. The second one, number 2, beta of x plus 1 comma y is equal to x over x plus y, beta of s comma y. That is the number 2 thing. Number 3, beta of s comma y plus 1 will also be y over x plus y, beta of s comma y. Number 4, we need to show the integral from 0 to pi over 2 of sine p minus 1 theta cos q minus 1 theta. The theta is equal to gamma of p over 2 gamma of q over 2 all over 2 gamma of p plus q over 2. Number 5, we need to show the integral from 0 to pi over 2 of sine p minus 1 theta. The theta is also equal to integral from 0 to pi over 2 of cos p minus 1 theta. Theta is equal to root pi over 2 multiplied by gamma of p over 2 over gamma of p plus 1 over 2. Number 6, integral from 0 to 1 of dx over square root of 1 minus x raised to power n is equal to gamma of 1 over n over gamma of 1 over 2 plus 1 over n multiplied by root pi over n. Hence evaluate hence compute integral from 0 to 1 of dx over 1 minus s raised to power 4 raised to the power of 1 over 2. Solution. Number 1, beta of 1 plus n, 1 minus n. Of course, the relation from the relationship between beta and gamma function, I will just use this This will become gamma of n plus 1 or 1 plus n, gamma of 1 minus n obviously, all over gamma of 1 because n plus, all over gamma of 2 because n plus 1 minus n is equal to 2. So gamma of 2 is 1 factorial and that's 1. So I have gamma of n plus 1, gamma of 1 minus n. And don't forget gamma of n plus 1, gamma of n plus 1 is n gamma of n. So that is n gamma of n, gamma of 1 minus n. So whenever you have gamma of n, gamma of 1 minus n, that was the second thing we proved. This one will always be equal to n multiplied by pi over sine n pi. So the answer is n pi over sine n pi. Line number 2, I have beta of x plus 1 comma y. This one will be equal to beta, this one will be equal to gamma of x plus 1, gamma of y, all over gamma of x plus y plus 1. That is what I am going to have. So this one will be s gamma of x, gamma of y, over this one will be s plus y, gamma of s plus y. So that will be s plus y, gamma of s plus y. So this one will just be equal to x over x plus y. I have gamma of x, gamma of y over gamma of s plus y. That's just beta of s plus beta of x comma beta of y. Beta of x comma y. That is what it will be. That is what I will have. I've done number 2 that way. Now number 3. Number 3, I have beta of s comma y plus 1. I want to prove that it's equal to this. I can use the way I solve for 2. I can solve similarly for 3, or I can say this one by symmetric property. This is also equal to y plus 1 comma s. Then I just use the result I have in 2 straight up. What I have in 2 is beta of s plus 1 comma y. So I just replace s with y and y with x. So that's why I have y plus 1 comma s. So this one I'll just replace, this one will now be y over y plus x. That's still the same thing as s plus y. Then I have beta of y comma s, and beta of y comma s is still the same as beta of s comma y. So I'm done with number 3. Number 4. Now this one, recall that this is where I'm going to start from. Recall that the polar definition of the beta function, beta of m comma n, I have to put over 2 here, is equal to integral from 0 to pi over 2 of sine m 2n minus 1 theta cos 2n minus 1 theta, the theta. So now since I have this, so I'll just let m to be equal to p over q, p over 2. If I let m to be p over 2, this one will be p minus 1, and which is what I will have here. The same thing for q, and the n to be q over 2, and that's all. So when you put it here, you will have we are going to have integral from 0 to pi over 2 of sine p minus 1 theta cos q minus 1 theta is equal to, this is 1 over 2 beta of m is p over 2, that is beta of p over 2 comma q over 2. So to finish this up, this one will become 1 over 2 gamma of p over 2 gamma of p over 2 all over gamma of p plus q over 2. So that is what I have here, which is the answer. That's all. Now for the next one, number 5. Number 5 wants p to be 1 from 4. Let p be 1 from 4. If we look at 4, from 4, let q be 1. That's all we need. So if you let q to be 1 from 4, you have integral from 0 to pi over 2. You will just be left with sine p minus 1 theta. Then this one, there will not be, when q is 1, you have 1 minus 1. 1 minus 1 will be 0. Cos 0 is, cos raised to the power of 0 is 1. So I have sine p minus 1, the theta is equal to 1 over 2 beta of p over 2 comma 1 over 2. So the same applies to this one. Don't forget integral, note integral from 0 to pi over 2 of cos p minus 1 theta as well will just be actually similarly from this 1 over 2 beta of 1 over 2 comma p over 2. That is what we are, and this one are the same because beta function is symmetric. That is, beta of p over 2 comma 1 over 2 is equal to beta of 1 over 2 comma p over 2. That is why they say this and this are the same. That is why they say sine p minus 1 theta cos p minus 1 theta. That's why they equated it, because they are same. And what we just need to do is we just need to get the value of this in terms, like we have to use the value of this in terms of gamma. That means this and this are equal. So integral from 0 to pi over 2 of sine p minus 1 theta d theta is equal to integral from 0 to pi over 2 of cos p minus 1 theta d theta is equal to 1 over 2 multiplied by, this is gamma of 1 over 2 multiplied by gamma of p over 2 all over gamma of p plus 1 over 2, because p is 1, p plus 1 over 2. So gamma of 1 over 2 is square root of pi, and that solves the question. Gamma of 1 over 2 is root pi, so I have root pi over 2, gamma of p over 2 all over gamma of p plus 1 over 2, and that's all. So if p is an integer, if it's even, you can compute the value for this, and if it's odd, you can also compute the value for this. You know how to compute the gamma function. Oh, I just rub off question 6 and 7. So I need to rewrite it. Number 6. Number 6 is saying that we should integrate from 0 to 1 of ds over square root of 1 minus s raised to the power of 4. That is s raised to the power of n. and I'm told to actually show that it's equal to gamma of 1 over n over gamma of 1 over 2 plus 1 over n multiplied by root pi over n. Solution. So what I will just do is I will let t to be s raised to the power n. So x should be equal to t raised to the power of 1 over n. So differentiate when s is 0, t is 0, when s is 1, t is 1. So ds is 1 over n, t raised to the power of 1 over n minus 1 dt. So this one will now be equal to integral from 0 to 1 of 1 over, this is 1 minus t now, 1 minus t raised to the power of 1 over 2 multiplied by ds. ds is 1 over n, t raised to the power of 1 over n minus 1 dt. So I will have 1 over n to come out because it's a constant. Integral from 0 to 1 of this one will be t raised to the power of 1 over n minus 1. Then this is 1 over t, 1 minus t raised to the power of 1 over 2 minus 1 as well. 1 over 2 minus 1 will give me negative 1 over 2. And negative 1 over 2 is exactly 1 over 1 minus t raised to the power of 1 over 2. That is why I've written that. So by the definition, by the polynomial definition of the gamma function, of the beta function, this one will just be exactly 1 over n beta of 1 over n, comma 1 over 2. So this is 1 over n gamma of 1 over n gamma of 1 over 2 over gamma of 1 over n plus 1 over 2 from what we got from the relationship between beta and gamma function. So at the end of the day, integral from 0 to 1 of ds over square root of 1 minus xn will be equal to 1 over n. Gamma of 1 over 2 is square root of pi, so I can write with pi over n, then multiply by gamma of 1 over n over gamma of 1 over n plus 1 over 2. Gamma of 1 over n plus 1 over 2. That's what we have, and that's all. That's what we have there. So, what is the next thing? The next step we should evaluate, and so otherwise we should evaluate integral from 0 to 1 of dx over square root of 1 over 1 minus s raised to the power 4 raised to the power of 1 over 2. Right? Yes, so that means this is the question. Just put n to be 4. Substitute n equal 4 in 5 in 6a. Substitute n to be 4. Maybe I should call it 1 in 1. So this will be equal to integral from 0 to 1 of ds over 1 minus s raised to the power 4 raised to the power 1 over t equal root pi over 4 multiplied by gamma of 1 over 4 over gamma 1 over 4 plus 1 over 2 will give me 3 over 4. I can leave my answer like this, or I can leave my answer in terms of gamma of 1 over 4. So this should be the answer. Or better still, I do this way with pi over 4 multiply both numerator and denominator by gamma of 1 over 4. So that this one will become gamma of 1 over 4 all square over gamma of 3 over 4 gamma of 1 over 4. Gamma of 3 over 4, gamma of 1 over 4. Don't forget this one. Gamma of 3 over 4, gamma of 1 over 4 will then be equal to pi over sine 1 over 4 pi. Sine 1 over 4 pi is root 2, 1 over root 2. So this one will now be pi root 2. That is what I'm going to obtain. So, to finish up, you just let, so that means that integral from 0 to 1 of the x over 1 minus x raised to the power of 4 raised to the power of 1 over 2 is equal to root pi over 4 multiplied by gamma of 1 over 4 all square over pi root 2 over pi root 2. So this one will just be gamma of 2 pi 1 over 4 all square over 2 over 8 pi. And that's the answer. Thank you very much.